Hello everyone. Today we're going to start Unit 1 of Algebra 2. The first lesson is characteristics of functions. The essential question is what are the important parts of graphs? So we're going to talk about the important parts of the graphs today. First, let's go over some vocabulary. Relation. Relation is when you have two sets of, let's say, x and y, and they are related together. Let me show you an example. I have two sets of x and y. Each of them have some elements, like these, for example, and they are related, like this. This element is related to this one. This one is related to this one. This one is also related to this one. So you see some relations between the elements of these two sets. That's called a relation. What is function? Function is a relation where every x has only one y value. So you see, in this example, we have this element which is related to two different elements. But if we have a function, each element of x is related only to one element of y. So you see only one arrow going out from each element of x to y. What is y-intercept? That's where in the relation the relation crosses the y-axis. And in this case, x is 0. What is x-intercept? That's where the relation crosses the x-axis. And then y is equal to 0. Let me show you an example so you can understand this better. Okay, so in this example, you see a graph. This is a graph of a relation. And I see that this graph is crossing x and y-axis at some points. Where the graph is crossing the y-axis, that's called y-intercept. At this point, x is 0, and y is this point. What is it? 1, 2, 3, 4. So y is equal to 4. So I can say the y-intercept is 0 and 4. X is always 0 for y-intercept, and y is this value in this case. It's 4. Okay, what is x-intercept here? X-intercept is where the graph is crossing the x-axis, and that's this point in this case. At this point, y value is 0. So you see the y value is 0. But what is my x value? It's -1, -2. So it's my x value is -2. So x is -2 and y is 4. Notice that y and x-intercept are points. So in order to write them, I need to use an ordered pair. So you need to use an ordered pair to write them like in the correct notation. X-intercept has another name that's called zeros. So it's the same as x-intercept. It's the same as x-intercept. So if I ask you what is the zero of this relation or this graph, you're gonna say -2 and 0. That's the zero of this graph. It has another name also, which is called solution. So if I ask you, what is the solution of this graph? What is the zero of this graph? What is the x-intercept of this graph? You're going to say -2 and 0 for all of them. They're all the same. Now, let's see, is this function continuous or discontinuous or discrete? A function is continuous when you use your pen. Let's say, for example, I'm going to use my pen and follow the path of this graph. So as I'm following, do I need to pick up my pen at some point and go to the rest of the graph? If yes, then your function is discontinuous, like this case that we have here. So I'm following this path, but at some point I have to pick up my pen and then go back here again and continue. So this is discontinuous. If I didn't have to pick up my pen, then it would be continuous. For example, let me show you another example over here. If this is my graph, okay, so see, I'm starting from here and just going, following this path and going to the end. I didn't have to pick up my pen. So that means this function is, or this relation is continuous. We'll talk about discrete later. Okay, so continuous function is when the values are continuous across a domain. So all the values are continuously coming one after each other. We don't have to make a jump. Discrete function is when the values are discrete or separate and they are not continuous. What does that mean? That means, for example, here I have a relation that has just some points, discrete points. The points are separate, they are not connected at all, so we call this a discrete function. What is this continuous function? That's when certain values appear to be missing, like this one over here. You see some certain values of y are missing over here. I have to make a jump to go to the rest of the graph. So that's why we call this discontinuous. Okay, here we have another example of a relation. This time we're showing the relation in a table that has some sets of, like, some numbers as x and some numbers as y. I'm trying to find the y-intercept here. We know that when we have y-intercept, then x is equal to 0. So I'm going to look for a relation, like for a pair of numbers that have x equal to 0, and that's this one. So I can say the x-intercept here is 0 and 5. I'm sorry, the y-intercept. I apologize. Now, what is x-intercept? We know that if we have an x-intercept, then y is equal to 0. So I need to look for a pair that has y as equal to 0, and that's here. So I can say the x-intercept is 6 and 0. What are the roots of this relation? We know that the roots are the same as x-intercept. So I'm going to say the same thing that I had as x-intercept over here. This is going to be my root as well. Now, is this function continuous, discontinuous, or discrete? This is going to be discrete. Why? Because we have some separate numbers. We have some separate numbers like -4 and 7, 0 and 5. I can show them for you on a number, on a coordinate plane. So see, for example, -4 and 7. It's going to be somewhere like here, for example. 0 and 5. It's going to be, let's say, here. -1 and -10 here. -5 and -3, let's say here. 6 and 0. So you see, we have just some points, separated points. Nothing is connected, so we call this a discrete function. Now, what is an increasing function? Increasing function is when, as the x values of a function are getting larger, the y values also get larger. I can show you an example in a table, x and y. So I have 2, 4, and 5 here. So as you see, the x values are getting larger, 2, 4, and 5. And the y values are, let's say, 10, 12, and 19. See, the y values are also increasing. So this is an example on a table. On a graph, how would that look like? For example, I have a graph that looks like this, okay? So as you see, as I'm moving from left to right, keep in mind, we always move from left to right because the small numbers are on the left side and the bigger numbers are on the right side. So I always move from small to. Okay, so as the x values are increasing, I see that the y values are increasing as well because, like for example, this one is 1 and like this is 2 and 1. Then this one is 3 and 2. This one is 4 and I don't know, let's say 4. Okay, so the x values are increasing and also the y values are increasing. As I look at the graph, I see that the path over here is going up. So this tells me that this function is increasing because it's going up. As I'm moving from left to right, the graph is going up. Now, what is decreasing function? Is as x values get larger, the y values get smaller. So the table could be like this. I have 2, 4, and 5, but this time the values of y are going down, 19, 12, and 10. You see, the y values are going down. How would the graph look like? It would be something like this. As I'm moving from left to right, so I start from the left side of the graph, I see that the y values are going down. So this is a decreasing function. Okay, so let's look at this example. On this graph that you see, we are trying to find the y-intercept first. Okay, so let me erase this first. Okay, I'm trying to find the y-intercept. I know that y-intercept is when the graph is crossing the x-axis, and that's here, this point. X is 0, and what is the y value? 1, 2, 3, 4. So it's 0 and 4. This is my y-intercept. What are the roots or solutions? We know that they are both the same, and they are both the same as x-intercept. So I just need to see where the graph is crossing the x-axis. It's crossing at 2 different points. One of them is this one. At this point, x is -2, and y is of course 0. And at this other one, x is -4, and y is 0. And as we said, they are both the same. Solution and roots are the same, so I'm just going to copy the same thing here. Now, is this function continuous or discontinuous? Okay, I'm going to try that. I'm going to use the pencil test. As I move let's say I put my pencil here, and I just follow the path. You see, do I have to pick up my pencil? No. So that means this is this, and this is continuous. Now I want to see on what interval or where does my function increase. So where is my function increasing? I'm going to look from, like, I move from left to right. I also want to find a decreasing area. So I'm going to move from left to right. Okay, as I start from the left side, what is my function doing here? Of course, it's decreasing. Yeah, it's going down. So starting from this point, it's going down until it reaches here. And suddenly at this point, it's going to go up. So first of all, I have a decreasing area here. So on this interval, I'm going to say my function is decreasing. How do I show that? I'm going to write the x values. I say where x is, like at this point, it's -1, -2, -3, -4, and -5. So from x equal to -5 to x equal to this point, which is -3. Between these 2 points, my function is decreasing. Okay, after that, from here, as I'm moving from left to right of my graph, I see that the graph is going up until this point. At this point, it's going to change the direction. So I would say from -3, when x equal to -3, 2, x equal to 1, my function is increasing. Again, another part, it's going to go down from here because it changed the direction. Goes down to somewhere like, let's call this one. My graph is not very accurate, but I'm going to say at this one, it's going to go down. So I say from x equal to 1 to x equal to 2, it's decreasing. So x equal to 1, 2, x equal to 2. Notice that I only write the x values here. So I say from this point to this point, my function is decreasing. From this point to this point, my function is increasing, and so on. Okay, so the last part, from here to the rest of the graph, it's going to go up. So it's increasing. So I say from 2 to 4, 3, 4, 5. So x2 to x equal to 5, it's increasing. So that's about increasing and decreasing. Okay, now we have another example. Let's say I have a donut here, and I want to divide it into half and give them to my friends. Okay, so let's see what happens. Will I ever entirely run out of my donuts? Let's see. So the first time I divide my donut to half. So at first I have one whole piece of donut. So I can say I'm going to write, show the like amount of donuts that I have on this graph. So I'm going to say the x-axis is the number of slices, and the y is the number of donuts. Okay, so at first I have one whole piece of donut. So I'm gonna mark these in this way. Let's say I have these numbers over here. This is 1, and this is 1/2, and this is 1/4. I will explain to you why am I giving the numbers like this form here. This is 1, 2, 3, 4, and 5. Okay. So at first I have one whole donut. Okay, so at first, at the beginning, I have one donut. When I divide that to half, I'm going to have, like the next time, I'm going to have 1/2 of it. So the next point is going to be here. Next, I'm going to divide the other half to another half. So the next time, I'm going to have 1/4 of that. You see, this is what I have next time. So it's going to be here. The next time, I'm going to again divide this to another half. So this is what I have next time. Okay, so the point is going to be here. For the third time, again, half of this point. It's going to be somewhere like this. Then I'm going to divide this again to another half. Okay, so then this is what I have left. Okay, so the next time, for the fourth time, I'm going to have half of this again. So it's going to be here. Next time, again, I'm going to divide this to another half. Okay, well, of course, this is not really half, but okay, like this. Again, another half. So for the fifth time, it's going to, again, half of it. So as I continue doing the same thing, my number is going to get smaller and smaller. So theoretically, I can continue dividing this donut forever, because always, no matter what small number I have, we always have another small number smaller than this one. So basically, the graph is going to look like this, and it's going to continue forever. Let me fix this again. You see, this is going to continue forever, and it will never reach to 0. Why? Because we always have infinite number of small numbers. Whatever is your number, you can always find another number which is smaller than that. So it's going to continue forever. So we can say this graph is going to approach, let me fix this, approach zero, but never passes zero. Why? Because we always have another smaller number. But practically, I'm not able to divide to very like those little small pieces. At some point, I have to stop uh, cutting my donut into half. So what is this situation called? When my function is getting close to something, approaches to that point, but never passes through that point. That's called an asymptote. That's a line that a graph approaches as the value of a variable becomes extremely large or extremely small. So you see, as my y value is getting extremely smaller and smaller, so it's getting close to zero, but doesn't ever pass zero, never gets equal to zero. So that's called an asymptote. So in this case, I can say I have an asymptote which is called this line, and it's called horizontal asymptote. And the equation of that is y equal to 0, because your y values are getting closer and closer to 0. Okay, so now let's talk a little bit about symmetry. Let's see, where would you fold these letters in order to have symmetry? Think about this. For example, the first one, if I have a letter A, I can use this line to divide this letter to half. Well, of course, these shapes are not very like accurately symmetry, but let's imagine this A is symmetry. So I can say that using this line, I can fold this letter so I will have the two sides exactly similar to each other. Can I do the same thing for R? I don't think so. So if I divide it like this way, it won't be equal. The two sides are not going to be equal. If I divide it this way, fold it this way, again, they're not equal. For the B, maybe I can say if I divide, like fold it this way, then the top and the bottom side could be similar to each other. For X, yes, I could divide it this way. I could fold it this way, or even this way, or even this way. So in each case, if I fold this letter, I will have the two sides exactly equal to each other. So we call this symmetry. We have a definition here. Reflectional symmetry is symmetry that occurs when half a figure is a mirror image of the other half, as you saw here. What is the axis of symmetry? That's the same line that made this image divided to equal halves. So it's a line through a shape, so each side is a mirror image. Okay, let's talk a little bit about vertical and horizontal lines. This is just a quick review. We have learned this before. When you have a horizontal line, the slope of that line is 0, and the y values are all equal. If you have a vertical line on the coordinate plane, then the slope is undefined, and all x values equal to each other. Okay, so for example, on the coordinate plane, I have this line, this is horizontal line. See, all the y values are equal. Or if I have a vertical line on the coordinate plane like this, all the x values are equal to each other. And the slope here is undefined, here is 0. So this was just a review for you. Now let's go back to axis of symmetry here. We have some graphs. We want to know if we have an axis of symmetry in these cases or not. Okay, so if I look at this shape, I see that I can use a line to divide this shape, this graph, into two halves, that each half is the mirror of the other one. And that's like for this one is here. Okay. So I say that yes, we have an axis of symmetry, and the equation for this axis of symmetry is x equal to -2. So you see here we talked about the vertical line. This axis of symmetry is vertical, so the equation is going to be x equal to -2. That will be the equation of a vertical line. For this one, so for this one we said yes, we have a symmetry and it's at x equal to -2. But for this one, we do not have any axis of symmetry because there is no line that I divide like the shape into two halves and I see that the two halves are like similar to each other or symmetry or image of each other. So we can say that there is no symmetry here. How about this one? Yes, if I just get a closer look, I will say that if I use this line over here, I'll see that this half is the mirror of the other half on the left side. So we have symmetry, yes, and the symmetry is at x equal to 1, 2, 3, 4, -4. Okay. Then we have rotational symmetry. That's when a figure can be rotated less than 360 degrees around a central point and looks the same. What does that mean? So let's say this is my original graph, okay? So I want to know if I have this graph and I try to rotate this graph, am I gonna get a rotational symmetry or not? So if I rotate this around a central point like this one at the origin, less than 360 degrees, am I gonna have the same shape or not? Okay, so for example, here, this one, I'm going to rotate this. See, I'm rotating this. If I rotate this exactly 360, it's going to be exactly the same thing. So we don't call that symmetry because 360 is always going to be on the original shape. So I don't call that symmetry. But what if I turn this 90 degrees? Okay. So I'm going to rotate this for 90 degrees. From here, I'm going to rotate it 90 degrees, and it's going to look like this. Like from here to here, let's say it's 90 degrees. So it's going to look like this. So it's not going to be exactly the same thing that it was before. So I'm going to write that here for you. You see, I have this graph here. I'm going to rotate this for 90 degrees. It's going to look like this. Is it the same thing that it was before? No, it's not. So we can say that this one is not a rotational symmetry of 90 degrees because it's going to look like this. If I rotate this shape for 90 degrees, it's going to be like this. So it's not the same thing as it was before. Okay. This time I'm going to rotate this for 180 degrees. So 180 degrees is going to be like this, and as you see, it's going to look exactly like what it was before. So I can say yes, this one has a rotational symmetry of 180 because as I rotate this, the rotated shape is going to look exactly the same as it was before. Okay, now I'm going to rotate this for 270 degrees. So that means it's going to go here for 180 and then continue for 270. It's going to be like this. So it's not the same thing that it was originally. So we say this one does not have a rotational symmetry of 270. So I say no, because the rotated shape is going to look like this. Okay, so in summary, we can say reflectional symmetry is when it looks the same when reflected across a line, and rotational symmetry is when the shape looks the same when rotated around a point. So this was today's lesson. And here's your homework. Your homework is going to be assignment 1.1, which is a Google form. I will share this to your Google Classroom. Look for that and return it in as soon as possible. Have a great day.